Hello everybody, I'm currently on my iPad since my phone is broken and I can't live stream it. So I'll record the lessons here and then upload them for you to see. Okay, so we're on to Unit 2 now. This is where we'll really start to get into the heart of analyzing functions. The main object in Unit 2 is going to be the tangent line. We're going to be talking all about the slope of the tangent line to a curve and how finding the slope and analyzing the slope of the tangent line tells us about the properties of a function. And this is the very first chapter, so we're going to talk about what is the differential coefficient and derivative, which is all related to the slope of the tangent line. In order to do that, first we have to go back a little bit. I think in Math 10, we learned the slope formula between 2 points, and in fancy terminology, we call that the average rate of change. Now, the average rate of change is defined by delta y over delta x for function y equals f of x. So this triangle symbol has the name delta, and it means change in. You might have seen it in physics class as well, and it follows an order. So if you're going to do delta y over delta x, then it has to follow the order final minus initial. So if this is f of b minus f of a, then the denominator has to follow b minus a, right? That's just the slope between 2 points. You have to keep the order. We'll talk about this in just a moment. This is what you get when you try to preserve delta x. If you want the denominator to be a single number, then you want the numerator to look like this. And I'll visualize that in our drawing here. Okay, so if we switch over to the drawing, this is some notes that I made in preparation. So if you see here, this is A and this is B, and here the blue curve is our function f of x. Now, the average rate of change that we just did, the slope of the line between 2 points, we call that the secant line. Secant, the sec in secant means divide, and you can see this line sort of, divides the curve, but most importantly, it's passing through 2 points on the curve, x equals a and x equals b. Now, about the second picture, so what does this mean? Well, if we treat the offset between a and b, and we treat that as delta x. So delta x is literally b minus a, right? We've assigned that final minus initial, right? And if we set that as delta x, then b is essentially going to be a plus delta x. Now, we're assuming that delta x is positive because I drew b to the right side of a, but it stays the same even if b is on the left side of a. Delta x would be negative, and then the formula would stay the same because you're keeping the order. Now, the function value at b is going to be f of a plus delta x, right? And then the function value at a is still going to be delta f of a. So you get this expression. These two are the same expressions. They're equivalent to each other. Now, if we go back to the notes, the instantaneous rate of change, or the differential coefficient. So this is new, right? As you can see, we denote that by f prime of a. So the slope of the tangent line, that's the instantaneous rate of change. Now, in geometry, if we think about like circles, we just defined the tangent line to be, hey, it intersects the circle, it intersects the curve at just 1 point. Now, we could, that geometric definition is still valid, but it's pretty difficult to generalize to any type of function and any type of curve. We need a really sound algebraic system to define the slope of the tangent line. So the idea here is that we have 2 points, right? As long as we have 2 points, we can figure out the slope between them. That's no problem. So what if we fix the first point, since we're curious about the tangent line at A, we fix the first point, and then we move the second point closer and closer to the first point. We move B closer and closer to A. Now, doing this, remember, when we first talked about limits, I emphasized that when you're taking a limit, you're getting closer and closer to something, but not actually getting there. This is an exact application of that logic, right? If we only have 1 point, then there are infinitely many lines going through that point. We can't define a slope. But as long as we have 2 points, that are getting close to each other but not actually touching each other, then the slope of the secant line will gradually approach the slope of the tangent line, which is labeled in red here. So the logic is the limit of the slope of the secant line as the 2 points get closer to each other is the slope of the tangent line. And that's how we algebraically define and think about tangent lines in calculus. So if we go back, as you can see, we see a limit expression. The change in x goes to 0. Delta x goes to 0, obviously, because why? We're sliding this point towards that point. B is going to A, so obviously delta x will get smaller and smaller and smaller, and it will approach 0. Now, there's two limits here. So if we use this form, we can get delta x goes to 0 of f of a plus delta x minus f of x over x, right? This is the average rate of change, and we're sending delta x goes to 0. Or alternatively, we can use the first form and just simply say, hey, I'm going to move this point, if we go down, I'm going to move this point, I'm going to send this to A. So if you can see here, we have x goes to a of f of x minus f of a divided by x minus a. As you can see, both of these are 0 over 0 limits, because if we plug in 0, it's going to be f of a. This should be a. Sorry. This x should be a. You can replace that in your notes. But if we plug in 0, it will be f of a minus f of a divided by 0. And here it will be f of a minus f of a divided by a minus a. So it's all a 0 over 0 limit that gives us the slope of the tangent line. And that is called the differential coefficient, or the instantaneous rate of change. Okay, so what we can do now is we can try evaluating limits using the differential coefficient, right? So you'll see a lot of limit expressions that look similar to this, f of a plus delta x minus f of a divided by delta x. Now, it is important to equally both be familiar with these two expressions. Delta x is usually, a lot of the times we represent this by a single letter called h, as you can see down here. Okay, so let's take a look at a few examples now that we learned how the tangent line is defined and how we can manipulate it algebraically. Because as you've seen in the limits and continuity unit, manipulation and modifying the expression to get what we want is very important in solving more difficult problems. So in number 1, we have f of a plus k times h minus f of a divided by h. Now remember the definition of the tangent line, right? It's the limit of the secant line, the slope of the secant line. So if this is a and if this is b, then in the denominator, we have to have that respective change of large A minus large B. Now, large A and large B might be anything, but it's important that the numerator and the denominator match, right? So that way we know that it's the limit of the slope of the secant line, the average rate of change. Now, if you see here, the stuff inside the brackets, A plus KH and A, so let's subtract that. A plus KH minus A is equal to K times H. So in order for this to be a slope of the secant line, the average rate of change, we have to make the denominator KH. But as you can see, we only have H, so we need to modify it. So we've put down a K here, and then we've multiplied a K here to cancel that out. And this becomes the average rate of change. And limit H goes to 0. See how the numerator goes to 0, and the denominator goes to f of a minus f of a. That means that these 2 points are getting closer together towards x equals a, right? Because they both go to a, right? If this goes to 0. Okay, then this limit itself is going to be f prime of a, but we have that constant k multiplying, so it's going to be k times f prime of a. Number 2 is a example of the other way to visualize, to write this down, right? So here we have x going to a of f of x squared minus f of a divided by x squared minus a squared. Now, it's the same thing here. anything could be inside these brackets, and that's okay as long as the denominator matches that. So if this is f capital A minus f capital B, where capital A and capital B could be anything, the denominator has to be capital A minus capital B in order for this to be the average rate of change. And here, it's going to be x squared minus a squared, so it matches that perfectly. So we can just directly say that this is going to be the average rate of change, and the limit of that as x goes to a is f prime. And when you plug in x equals a, notice how this goes to f of a squared, and this also goes to f of a squared. So the final answer is going to be f prime of whatever thing it's approaching to, right? Keep this picture in your mind, right? This is going to be very important. So technically, what we're doing here is this is x squared and this is a squared, and we're sending x to a and making this point go closer and closer to that point and getting the tangent line there. Okay, the next limit looks kind of complicated. If you plug it in, it's going to be an infinity times, this goes to 0. So it's going to be an infinity times 0 limit. But if you think about it for a little bit, if we substitute x with 1 over t, then we can rewrite it as 1 over t times f of a plus t minus f of a. And as x goes to infinity, t goes to 0, so limit t goes to 0. And as you can see, this is literally the definition of the derivative, right? A plus something minus a over something as that something goes to 0. So it's just a matter of unpacking and trying to figure out what this expression actually is. So this is the equivalent expression to f prime of a. And then the last one, we have a plus h, a minus h. Although it looks a little bit different and a little bit complicated, it's the same principle. If this is capital A and capital B, then the denominator has to match capital A minus capital B for this to be a average rate of change. So a plus h, a minus h is 2h, right? So we're supposed to have 2h, but we only have 1h. So we're going to put a 2 here and then multiply it by 2 as shown here. So this is just going to be 2 times f prime of a. Okay, with that, let's go to the workbook. I think number 1, you guys can try on your own, right? It's just the average rate of change, right? It's just the slope between those 2 points where x equals a and x equals a plus 2. Okay. Let's try number 4 for now. For 0 larger than a less than b, which statement is true? F prime A, F prime B, and then this is, as you can recognize, the average rate of change from A to B. So let's go to our graph and draw those in. The average rate of change is the slope of the secant line. The instantaneous rate of change is the slope of the tangent line, F prime of A and F prime of B. Okay, so it's close to that, right? And as you can see, which one is the largest? So we have to look at the positive one first. F prime of B will be the largest, followed by the average rate of change, followed by F prime of A. So your answer is simply D. Okay, so that's simple enough. Let's take a look at number 6. For differentiable function fx, limit f of 1 plus 3h minus f of 1 divided by 2h equals 2. Find f prime 1. Okay, so remember that whenever we find a derivative, we need this expression to match the slope of the secant line, or the average rate of change. Remember your capital A and capital B. 1 plus 3h minus 1 equals 3h. So your denominator should be 3h, right? So we're going to force it to be 3h, and then we're going to modify it afterwards. So 1 plus 3h minus f of 1 divided by, So we're going to make it 3h, but it was originally a 2, so we have to multiply 3 on the numerator to cancel out the 3, and then there was originally a 2 down there. So this is how you would modify. And this expression becomes f prime of, it approaches 1, right? F prime of 1 multiplied by 3 over 2, and that equals 2. So f prime of 1 equals 4 over 3. And there you go. Okay, number 7, I'll leave this one up to you. So there's 5 different scenarios and they all may or may not need their own type of modification. Okay, the rest, let's go back to the notes. Differentiability and continuity. If f prime a, the differential coefficient of function f of x at x equals a, exists, then f of x is differentiable at x equals a. Now remember, the derivative, the slope of the tangent line, is a limit. It's the limit of this or the limit of that, but we have to make sure that the limit exists, then it can be differentiable. If the limit does not exist, it's not differentiable. Okay, it also says that if function f of x is differentiable at x equals a, then it is continuous at x equals a. However, the converse statement is not always true. So it means that if you know that it's differentiable at a certain point, then you can be assured that it's continuous at x equals a. But continuity does not automatically imply differentiability. The easiest way to see this is what I call a sharp point. So if a curve, maybe a piecewise function, has this type of thing going on, right? And we want to know if the function is differentiable at x equals a or not. Now, remember, we're fixing one point here and we're sliding the other point towards this point. The left-hand limit would suggest that the point is on the left side and it's sliding over like that. The right-hand limit means that the point is on the right side and it's sliding over like that. So if we try to draw the tangent line from the left-hand side, it would approach something like this, something like that, and then eventually we would have a tangent line that sort of looks like that, at least the left-hand limit, right? And then for the right-hand limit, we would have something like this, right? Because the other point is from the right-hand side, and it's only going to get closer and closer from the right-hand side. If you look at the red and orange line, notice how their slopes are different, right? So we can say that the limit does not exist because the left-hand differential coefficient and the right-hand differential coefficient do not equal each other. So the limit does not exist. It is not differentiable. But notice how the function is still continuous at x equals a, right? There's no jumps or breaks. The left-hand limit, the right-hand limit, and the function value all equal each other. So these sort of sharp points are ones to look out for if you're looking for places where the function is not differentiable. Okay, so obviously, if it's discontinuous, then there won't exist a derivative at all, right? Because, you know, if the function is like that, the left-hand limit and the right-hand limit obviously won't match each other. So either it has to be discontinuous or sharp points. Those are the types of points where it would not be differentiable. And now we get to the derivative. Up until now, we've only thought about the tangent line at a single point, right? We focused on this single point A, we fixed this point, and we slid the other point toward this. But now we're going to generalize a little bit. If I'm given a curve, can I find the slope of the tangent line at any place that I want, right? Can I get an expression for the slope of the tangent line here, 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 and can I get a generalized statement of the differential coefficient? And the answer is yes. We call that the derivative of f of x. Now, this looks very familiar, right? We saw it over here, except this had a in its place, so a is a constant, but now we have x as the variable. The derivative is known as f prime x. It's kind of like a f dash of x. f prime x is defined as limit. We usually put this as h, so let me put an equal sign there. Limit h goes to 0 of f of x plus h minus f of x divided by h. So it follows the same pattern as the differential coefficient, except now the a, the constant, is replaced by x. So the derivative is a function. It's a function that gives you the slope of the tangent line at any value of x that you plug in, okay? So here I've written it in red. The slope of the line tangent to f of x at x equals, x equals x, right? So instead of x equals a, it's going to be whatever x that you choose. The reason that we don't use this particular type of limit for this is that it kind of gets confusing where x is like sliding over to x, right? You can't use the same variable twice. So we usually use this as our definition. So this is called the definition of the derivative. I think, in my personal opinion, it's like the second most important formula in calculus, right? But now we just don't memorize it. We now understand how it works, right? Because it's the generalization of the differential coefficient, and the differential coefficient was basically a fixed point, and you slide another point towards that fixed point. Okay, so that's the definition of the derivative. And now, yes, this is where it can get it's quite difficult to prove this, but I'll introduce the proof anyway. Okay, so the functions that we'll be talking about in this course is polynomial functions. Polynomial functions have this form, x to the power of n, where n is a natural number. The derivative of y equals x to the power of n is n times x to the power of n minus 1. Okay, so remember, the derivative is a function that gives you the slope of the tangent line at any x that you choose. So if you have a function like x squared, then its derivative is going to be, by this formula, 2x. So you can memorize it like this. The power goes down and subtracts by 1. So as you can see, the n goes down, so it goes down and it becomes the coefficient, and then it subtracts by 1 at the very end. If y equals c is a constant, then y prime equals 0. So the derivative of a constant function, remember it's just a flat line in the xy plane, you would expect it to be 0, right? Because if you choose any 2 points on a flat line, it's always going to be it's always going to have a slope of 0. Okay, in order to prove this, we need to know a couple of things. Now, I think I think it's a good idea to understand the proof once, and even if you don't memorize it the first time, it's totally okay to understand it and then move on and then keep practicing until it's more easier to understand later on. But I think understanding why a formula is made like this, right? Why is it n times x to the n minus 1? Understanding that, at least initially, is quite important. Okay, so in order to prove this, we have to know a couple of things. We need to know what the binomial theorem is. Okay. So the binomial theorem is what you use if you want to expand something like a plus b to the power of n. Okay, so binomial, the bi means 2, comes from, there's 2 terms in your brackets. There's a and there's b. I want to raise this to the power of n, where n is a natural number for our purposes. Okay, how can we expand this, right? So imagine a great way to understand this is that I have n brackets. right? If we write this all out, it's going to be n brackets multiplying each other. And from each of those brackets, I can choose A or B, right? I can choose A or I can choose B. And depending on that, I can get different combinations for the exponents for A and B. Now, what happens if I choose all A's? Then it's going to be n times A. There's going to be an n number of A's, right? So that's all multiplying. So that's going to be A to the power of n. If I choose, let's say, n minus 1 number of A's, and then the rest I'm forced to choose 1B, right? So n minus 1 A's and 1B, because I have to choose something from every bracket so I can multiply it all. That would get me A to the power of n minus 1 times B, right? But to get the coefficient, right, if we want the coefficient of A to the n minus 1 times B, I need to know how many times can I choose this specific combination. Because if I only need to choose 1B, then I can choose it from the first bracket, I can choose it from the second bracket, I can choose it from the third bracket, all the way to the last bracket. If I want A to the power of 3 times B to the power of n minus 3, I need to find the number of ways that I can choose 3 brackets out of the n brackets. And that's where combinations comes in. I don't know if you've seen this before. I hope you saw it. NCR. This is called a combination operator. The formula for this is n factorial divided by r factorial n minus r factorial, where if you haven't seen the factorial symbol before, n factorial is n times n minus 1. Obviously, n has to be a natural number. You multiply all the numbers until 1, okay? So this gives you the possible total number of ways of choosing r elements out of n elements without considering order. So let's say we have 10C2. What that means is this is going to give you the number of ways you can pick 2 elements from 10 elements without considering the order that you choose them in. That's why we have r factorial in here. We're dividing by the number of possibilities that you can arrange them. Because in some cases like this one, we don't really care about the order that we pick, right? As long as we got the number of B's and the number of A's, then we're good, right? So we don't have to care about order in this case. So with all of that being said, how can we expand this? The first term is going to be we pick all A's. Now, if we pick all A's, we're not going to be picking any B's. So let's write A to the power of n times B to the power of 0, right? Because we're not going to pick any B's. And the number of ways that we can pick n brackets out of n brackets is n combination n, NCN, times A to the n, B to the 0. So that's the first term. The next term is going to be we choose n minus 1 number of A's, and then the other brackets have to be B's. So A n minus 1 times B to the 1. And the number of ways that we can do this, we can choose n minus 1 brackets out of n brackets. Plus, we can keep going on. A to the power of n minus 2 times B squared, n minus 2 C n. And we can keep going on and on. So let me sort of move this over here. And then what we can do is we can keep adding this until we get to the final few terms. The final few terms is going to be a to the power of 1, b to the power of n minus 1 times nc1, right? We're choosing one bracket to represent a while all the others are going to be b, plus the final term is going to be nc0. We're choosing none of the brackets to be a, and the term is going to be a to the power of 0, b to the power of n. Okay, so now that we know how to expand these types of things, now let's take the derivative, okay? So the definition of the derivative is always f of x plus h minus f of x divided by h as limit h goes to 0. In this case, my f of x is going to be x to the power of n, where n is going to be a natural number. Now, if we plug in, if we replace f of x with the actual function, we're going to have x plus h to the power of n minus x to the power of n divided by h as limit h goes to 0. And now you realize why we spent all the time trying to expand and learn about the binomial theorem, because we literally have one right here. So we need to expand that all out, right? Because in this state, it's a 0 over 0 limit, and we can't do much about it, right? So limit h goes to 0. Let's expand this. Okay, x to the power of n h to the power of 0, ncn, right? Plus n minus 1 cn, x to the power of n minus 1 times h to the power of 1. And then we keep going until we get to, let's write the final two terms. Should we write the final three? Okay, let's write the final three. It's going to be x to the power of 2 times h to the power of n minus 2, and then it's going to be nc2 plus nc1 x to the power of 1 h to the power of n minus 1, and finally nc0 x to the power of 0 h to the power of n. So that's our expanded x plus h to the power of n using the binomial theorem. Okay, and then long line for the fraction. And then we're going to subtract x to the power of n. Okay, and then we're going to divide the entire thing by h. If you notice here, NCN, what's the number of ways that you can choose n elements from n elements, right? There's only one way, right? So there's one way of choosing n elements from n elements. So this is simply going to be x to the power of n. So this cancels out with this guy, right? Because NCN is just equal to 1. Okay, so as you can notice, the remaining terms all have a factor of h in them, right? So we can cross out the h, because we know that, in a limit, h is never going to actually equal 0. So we're going to cross this, cancel it out. So this will become h to the power of 0, and then h to the power of 1, all the way to h to the power of n minus 1, h to the power of n minus 2, and h to the power of, n minus 3, right? N minus 3, n minus 1. Okay. And now let's rewrite the limit. Limit h goes to 0. The first term is n minus 1 cn, x to the n minus 1, plus, and then the next term will be, so h to the power of 0 is 1, right? So that h won't be here anymore. N minus 2 cn, x to the n minus 2, h to the power of 1, right? Plus, we go all the way, nc2, x squared, h to the power of n minus 3, nc1, x1, h n minus 2, and finally, nc0, Okay, nc0 x to the 0 h to the n minus 1. And remember, h is still going to 0, except for the first term, except for this guy, right? Every other term in our expression has at least one factor of h in it, right? So it turns out when h goes to 0, all of these other terms go to 0, which means that they all disappear. And your final limit is, since the first term doesn't have any h's, we can take the limit symbol out, n minus 1 cn times x to the n minus 1. Now, a property of combinations is that, hey, I want to pick n minus 1 brackets out of n. That's the exact same thing to picking one bracket that you will not pick, right? So picking n minus 1 brackets out of n brackets is the equivalent to picking just one bracket out of the n brackets, right? Because you invert them, right? So a property of combinatorics, the combination operator, is that n choose r, I think people call it n choose r. N choose r is equal to n minus r choose r, because you can literally replace this with n minus r and n minus r, and this will become r factorial, right? So it's interchangeable, which means that this is equal to nc1 times x to the n minus 1. And how many ways can you choose one bracket out of n brackets? There's only n ways, right? So it's n ways times x to the power of n minus 1. And there you go. The derivative of x to the power of n, by the definition, leads to x to the n times x to the n minus 1. So there's a lot of complicated expansion, but in the end, almost everything goes to 0. So that's the proof involving the binomial theorem and the combination operator. Now, if you go to a full calculus class, you will probably prove this a little bit differently. This is known as the power rule, and what we proved is the derivative for natural numbers, if the power is a natural numbers. If you go to a full calculus class, you will see that the rule actually holds for all real numbers, right? But the tools to prove that are not in the scope of this class yet. But do know in the back of your mind that this power rule works for all real numbered exponents. The final thing to do is the derivative of a constant function, which is, pretty light compared to what we just done. H goes to 0 of constant minus constant over h, right? Remember that constant minus constant, this is not changing as x changes, right? So what's happening here is that we have a constant and the 2 points are getting closer to each other, and the slope is always going to stay the same as 0. Since h is going to 0, the denominator will never actually equal 0, which means that the entire expression will simply be 0 because of the constant minus constant. So the derivative of a constant function is 0. It's pretty obvious to see that. Okay, so this is the proof of the power rule and the derivative of a constant function. Okay, so going back to our notes, we've proven and seen how this works. A couple of algebraic properties for derivatives. A constant times a function, then the derivative will be constant times derivative, right? So you can factor out a constant and it will be no issue. If you want to take the derivative of two functions that are adding or subtracting, you can directly do so. F plus minus g, that goes to f prime plus minus g prime. So if you want to take a derivative of a polynomial function, you just want to evaluate each term separately and individually, right? Use the power rule for here, for each of these terms that you see. Okay, notice that I've left out f times g. Now f times g is a little bit different from plus and minus. You can only add and subtract functions and get the exact same value as adding the derivatives, right? If you're multiplying two functions, then the derivative of the function is actually not f prime times g prime, right? Remember that the derivative, definition of the derivative comes from the definition, the limit definition, right? It's a limit. So depending on the limit, the rules change. The product rule gives you the formula for taking the derivative of a function where you have two functions multiplying each other. As you can see, it's a little bit different from just simply f prime of x, g prime of x. Y prime is equal to f prime of x times gx plus f of x g prime of x. So here's how to memorize it. You take the derivative of the first one and leave the other one alone. You take the derivative of the second one and leave the first one alone, right? So you go by it one by one, and you take the derivative of the thing that you're looking at, and then you leave the other one alone. Okay, I think I'll finish off with the proof of the product rule. I know there's quite a lot of proofs today, but this is how we get to the formula, right? I think we all should be curious when we see new stuff, like how does this work, right? H goes to 0. Let's use the definition of the derivative. Right now, our function is y equals f of x times g of x. Okay, so you plug in x plus h, and you get this, right? Minus, you plug in x, and you get this, divided by h. Now, it's a 0 over 0 limit, and the modification that we're going to do, watch closely. What I'm going to do is, since I know the definition of the derivative for a single function, I'm going to try to utilize that as much as possible. What I'm going to do is I'm going to write f of x plus h, g of x plus h. But I'm going to write this. I'm going to add f of x plus h times g of x. Never mind, I'm going to subtract that. I'm going to subtract that because why? I'm going to factor these. I'm going to group these by f of x plus h so that we have g of x plus h minus g of x, and that will lead us to the definition of the derivative, right? Since I subtracted this, I'm going to add it back. And then we originally had our negative f of x, g of x. Okay, and this is all being divided by h. So that equals limit h goes to 0. And let's group this by f of x plus h. F of x plus h times we have g of x plus h minus g of x over h. Let's group that together. And then for these two, we're going to group it by g of x. So g of x times the numerator is going to be f of x plus h minus f of x, right? Okay, and now we can apply the definitions of the derivative, right? So these structures look very familiar, right? So limit h goes to 0 of f of x plus h, and this is going to be g prime of x plus g of x times f prime of x. Okay, and since h goes to 0, this will go to 0, leading to our formula f x g prime x plus gx f prime x. Okay, so that's the proof for the product rule. Okay. And I think we'll stop at the product rule for today. A couple things to note. if y equals f of x squared, then we can write it as f of x times f of x, apply the product rule, and get to 2 f of x, f prime of x. You don't have to remember this, however, since I think we'll learn more about these types of functions when we get to the chain rule. So let's go to our workbook and see what we can work out. So for homework, number 1 was homework. And number 2, as q, okay, so we have a, which is 1, 0. We have the function x cubed minus 1. Q is t, f of t, and q infinitely approaches a. So that's our literal definition of the slope of the tangent line at a. So we can take the derivative. Remember, its power goes down and subtracts by 1. So we have 3 times x to the power of 2, and then the constant goes away, right? We evaluate each term individually. F prime of x is 3x squared, so f prime of 1, since we're looking at x equals 1, is going to be 3 times 1 equals 3. So the slope will approach 3, and that's pretty chill, I think. The average rate of change, okay, so I encourage you to solve this. For homework number 5, if you've learned what log of x and sine of x looks like, you can attempt it. If you haven't, it's okay. You can skip over it. Okay, so we've done that. Number 7, I think it's pretty important how well we can modify the expressions for each of the limits. Okay. So number 16, we've proven it, so we won't go over this again. But let's see what we can do. Let's solve number 8 together, and then I'll give you number 9 for homework. Okay, polynomial function f of x satisfies this equals 1/2. Okay, so whenever you see a limit, you plug it in, this goes to 0, right? So the denominator goes to 0, but the limit exists, the numerator goes to 0. So we get the information that f of 2 has to equal 3 for the limit to exist. And now we have to go back to the limit, right? It's a difference of cubes, so let's factor this. X minus 2, x squared plus 2x plus 4. And then this is going to be f of x minus, okay, so I'd say it's pretty important note. When you get pieces of information like this, I think it's a good idea to scribble over f of 2 like that. Because if we do that, right, we can immediately recognize the derivative or the differential coefficient form. If this was just 3, we would have to make the connection that this is equal to that, and it isn't as visibly clear, right? So as x goes to 2, we have f of x minus f of 2, so replace this with f of 2 over x minus 2. And we can immediately see that that is the definition of f prime of 2 times the other portion. This goes to 4 plus 4 plus 4, which is 12, 1 over 12, and that equals 1/2. So therefore, f prime of 2 equals 6. And f prime of 2 times f of 2 equals 3 times 6, which is 18, right? So getting the habit of, if you recognize that this must go to 3, then replacing it with f of 2 will greatly help you in identifying those differential coefficient limits. Okay, number 9 for homework. Number 10 is quite a challenge, I think. If you try to spend like a couple minutes on it, it's okay if you don't see the solution. We'll go over that next time. Homework as a challenge. Okay, number 11, if you want to try proving this, you can. We'll go over the proof next time. Number 12 for homework. Number 13. Okay, 14 for homework. $15 for homework. Yeah, so once you learn the definition, I think it's pretty, there's a lot of problems that you can do. Okay, so why don't we cover up to number 15 for today's class, okay? And number 16, if you want to go over the proof again, if you want to rewrite that down, you're welcome to do so. Okay, so let's finish off with number 13 for today. Function f of x is that, and it's differentiable on the set of all real numbers. Find a plus b for constant a and b. Okay, so it's a piecewise function and it's differentiable on the set of all real numbers. Polynomial functions are differentiable on their domains. So what we really need to focus on is the boundary at x equals -2. So if we take a look at f prime x, right, we can say that, hey, this is going to be 2x plus a. Right? So the power goes down and it subtracts by 1. The derivative of ax is just a, right? Because the power goes to 0, or you can imagine the slope of a line is just, its slope. And then here it's going to be 2, right? When x is less or equal to the -2 and when x is greater than -2. Okay. I don't know what happened there. Okay, so now f prime of -2. So in order for the function to be differentiable, the left hand and right hand limit, so the left hand differential coefficient and the right hand differential coefficient have to be equal to each other. So on the left hand side, we are going to plug in -2 and get -4 plus a. And on the right hand side, it's always going to be 2. So therefore, a equals 6. And okay, so we got a equals 6, but we're also asked for b. Remember that in our notes, a differentiable function is always continuous. So if it's differentiable, it always implies that it's continuous as well. So we have to use the continuity condition as well. So let's plug in -2 to both sides. 4 minus 2a plus b, but now a is 6, so we know that, equals -4 on the right-hand side. So b equals 4 plus -4 plus 12, that's 8, minus 4 is 4. So b equals 4, therefore a plus b equals 10. Okay, so remember, when we're talking about differentiability, continuity is always implied, but not the other way around. All right, so the homework is displayed here, right? If we want to go over it again, number 1, number 3, number 5, number 7, number 9, number 10 is challenge, number 12, number 14, and 15 for next class. Okay, so great job getting through the first part in Unit 2. Things are going to get very, very exciting from here and onward. All right, I'll see you next class.